Hello, in this video we're going to examine some of the properties of the gamma function. Let's jump right in. So this is the definition of a gamma function. It's an integral from 0 to infinity of y to the alpha minus 1 e to the y dy, where alpha is a positive parameter, and it's represented by the capital letter gamma sub alpha. Gamma of 1 is 1, and this is how you prove it. So you put in 1 here and you get 0, and y to the 0 is 1, so it goes away. Integrate this, you get minus e to the minus y. You substitute in these. That, when you substitute it in, it goes to 0. Then it's minus this with y substituted in, and you get 1. So minus a minus 1 is 1. Now, the second property is that gamma of alpha is alpha minus 1 times gamma of alpha minus 1. Quick little proof is this. We have gamma of alpha, and then we do a u dv substitution, where y is alpha minus 1, dv is e to the minus dy. Then we calculate du and dv, the antiderivative, and we plug them in. So this is uv evaluated at the limits, and then this is vdu. So it's really minus this, but that negative comes out and makes it a plus. When you plug this in, this goes to 0 so much faster than that goes to infinity that the whole thing goes to 0. And when you plug in 0 here, you get 0. So we're left with just this interval, or this, integral. So here we'll pull the constant out front, and we're going to rewrite this alpha minus 2 to alpha minus 1 minus 1, and then e to the minus y. And we do that because that becomes the new parameter on the gamma function here. So it's alpha minus 1 times gamma of alpha minus 1. Okay. Now, why is that unique? Well, when alpha is an integer, then gamma of alpha just becomes alpha minus 1 factorial. And a quick little proof of that is we know that this relationship holds. We just showed it. And then we can repeat this again, and then we can keep repeating it until it becomes gamma of 1, because alpha is an integer and gamma of 1 is 1. So this is the product of these numbers, which is alpha minus 1 factorial. Gamma of 1/2 is square root of pi. And a quick little proof of that is you plug in 1/2 and you get, 1/2 minus 1, which is minus 1/2 in this. We do a substitution of y equals t squared divided by 2. So dy is equal to this. And you can back solve for, or take the square root of both sides to get the y to the 1/2, which is equal to t over the square root of 2. And we do that because we have a y to the half here. So now we substitute in dy is this. You plug in y for here and you get this, and then you plug in this for that, and you get that. So then this t and that t cancel, and then the minus 1/2 brings the square root of to the top, and we're left with e to the minus t to the t squared to the 1/2. So a lot of times in statistics, what we do is we try to manipulate integrals and summations to look like PDFs or PMFs, and then we know that it integrates to 1. So what we do here, that kind of looks like a standard normal distribution. If we had a square root of 2 pi over here. But if we do this, that means we have to multiply it. So the square root of pi here cancels with that one. And then since we already have a square root of 2 here, another one makes it 2. So those cancel with that. So we're multiplying by 1. And the standard, this is a standard normal, but we're only integrating from 0 to 1, and it is centered about 0. So this is 1/2, and 1/2 times 2 is 1, which then leaves the square root of pi. And this becomes relevant when you take, so this property, when you have fractions over 2, then gamma of 3 over 2 is square root of pi over 2. And a proof of that is we know that it's always alpha minus 1. So 3 over 2 is 3 over 2 minus 1, and then it's 3 over 2 minus 1. But then if you replace those, you get a half, and you get a half here. But here we said that was the square root of pi, so then we're left with the square root of pi over 2. Okay, well, that's all I have for today for properties of the gamma function. Hope you enjoyed it. Please like the video if you did, and subscribe so you don't miss more. Thanks, bye.